All right. Good afternoon, everybody. Hope you all have had a good time this week with the extended break, so to speak. I know it's been pretty nice to be able to get out and have a bit of winter time, play in the snow. My dog's been loving that. Maybe I'll find a way to share a couple photos at some point with you about that. But at any rate, so that we don't lose track of time and lectures, we're going to go ahead and do another lecture today. That way we don't have to catch up on any later. So today we're going to kind of pick back up where we left off about a week ago. And I touched on a little bit of this on Tuesday this week. So if you didn't see that, most of that lecture or session was practice with MATLAB and Excel. And I was giving some tips and some instructions there. But the first few minutes was on pH. So I'm going to gloss over that today, and I recommend you go back and take a look at that later. And by the way, I'd love it if you just said hi in the chat. That'll give you the confirmation that, oh, look, you can type something and I'll see it and all that. It's very easy to do. So, right now, for example, I just saw that several of you logged in, and I expect some more to show up. Your classmates will also be able to see it, so you could ask a question and everybody could see what's happening there. Okay, so thank you. Hello. And usually there's about maybe 2 to 5 second delay, probably. Perfect. Okay. All right. So today we're going to talk about the equilibrium reactions, and I love it. Thank you, guys. And I'm going to start by giving an example and taking us to a different YouTube page for a moment, because somebody put on a great example of how the speed of the equilibrium reactions work. And what I mean by that is the rate of a product moving to reactants or a reactant moving to a product. How long does it take until we get to an equal amount, or not even just an equal amount, potentially equal, but how long does it take until we get to an equal rate going either way? So that's the first thing I want to do for us, is just take a quick look here. There's a video here. I'm going to make sure the audio is working. Just give me a moment. Okay, that looks like I need to make one quick adjustment. Let's try that.
Demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here, that represents our reactant side of our process. And then of course we have our empty container over here that represents our product side of the process. So on any good reaction, when you start the process, everything's a reactant. So we all have all the water over here and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using 2 identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast, and at first a lot of water was switching sides going to the product.
Okay, so you kind of get the picture. He reached an equilibrium and it didn't take very long. The point I want to make here is that when we do equilibrium processes and problems in our class, usually we're skipping this part where it's taking some time to get there. But there's another illustration that he's going to show, and he's going to change the size of his beaker here, and I'll explain all that. It's basically changing the rate of his reaction. And so if he changes the speed at which the product can go one way or the other based on the size of his vessel there, that's going to reach a new equilibrium where we'll have the same total rate going across. And the illustration is very nice. I'm going to let him come back to that.
It has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay? So in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay? Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference, okay?
Okay, so I just wanted to share that quick illustration here. I think it's a nice little video to really highlight what we're talking about when we say we've reached equilibrium. Doesn't mean we have the same amount of stuff in either side, the products or the reactants, but we get to a point where the transfer is the same amount. For most of what we do, that process to get to that point is very quick. And I'm going to have another demonstration. I've got a little chemistry kit. If you can see behind me, I've got an aquarium here, and I'm going to check the pH of that aquarium and then adjust the pH of some of the water from that aquarium. So we're going to do a little bit of hands-on sort of a deal. But I'll save that for later once we've got a little bored from all the theory that we have to cover today. Okay, so that's the concept for what is this equilibrium about. The K then, what we could say is this is a little bit like the difference that we achieve based on the different size beakers. So something like the ratio of beaker size coming from that analogy, right? So it's that thing that tells us, this equilibrium constant tells us what portion is going to be products versus reactants. And the way we set that up mathematically, as we talked about last time, is the product of the products multiplied to each other divided by the reactants multiplied with each other. So the product of the products over the product of the reactants. And we have to include the superscripts if we have anything, any difference in the number of moles for the given reaction. Sometimes we will handle issues where we have some liquid or a solid, especially solids when we're doing precipitation or dissolution reactions, and we just handle that with a 1. There's a little more complexity as to why we can do that, or why we need to do that, but for the moment I'm just going to say we assume it's 1. So for example, when we set up our liquid water equilibrium, can dissociate in part into H plus and OH minus. When we set up the equilibrium constant for that, we'll call it Kw for K water. Using this convention, it would be one of the products, and this is the molar concentration with the brackets, to the 1 power, because we have an implied 1 there. Make sure you multiply here, times the OH minus, also to the 1 power. All of this divided by 1 because we assumed here. Because the H2O is a liquid right there. Okay, so this then is our equation, our equilibrium equation coming from this derivation for the equilibrium of water. So that's the deal with that part. And by the way, if my audio is not good or if I do something that causes some issue, please let me know. It looks like it's probably fine on my end, but I have a slightly different arrangement today than yesterday, or than Tuesday. Okay, so here's a little graph. It's pretty common when we talk about equilibria to see these two graphs really, and even that video that I showed highlights this just briefly. And it kind of shows what's happening in terms of the rate and the amount of stuff in the products and the reactants heading to that equilibrium. So if we look at the rates, when we achieve equilibrium, we have found equal rates. So when these two overlap, starting right about here, we're at equilibrium. Now, maybe it's a high or a low rate, but as soon as those rates equal each other, we've reached equilibrium. And remember, the rate is not a rate constant. So this does not mean our rate constants have to be the same. Usually when we write a rate reaction, it'll look something like this. We'll have we'll call this R1 equals K1 times the concentration to some power, depending on if it's first order or zero order or whatever. So we'll just say Kc for now, whereas R2 equals, take two different reactions on the same C. Let's have a -1 for K, or for the second reaction. So if those are our two rates, the Ks don't necessarily have to be the same. In fact, maybe in the one case, we have something else going on, and it's a 1 and a 0 here. So there are a lot of ways that the reactions of different sorts could have different rate constants, but find an equilibrium point where the rates themselves are equal. So I don't want to confuse you too much with this, so don't think too hard about that. I'm just saying that the rates are different than rate constants, different things can affect it, and the equilibrium is when the rates themselves find a value that they're the same. So equal rates would be like saying R1 equals R2. K1 is not necessarily equal to K2. Okay, so that's with the rates. The amounts was described very well with that little video, where the reactants and the products may have some very different amount in the respective pools, lots in the reactant, lots in the product, or whatever, but they've stopped changing. So at the same amount of time where we found equal rates is right about the same time where we see there's no more real change in our concentration or in our amount of stuff. So once that has stabilized, then that's another indicator that our system has reached equilibrium. Okay, so most of the chemistry, most of the thermodynamics, like I said, we're really dealing with everything to the right of this line. We can deal with the stuff on the left. The thermodynamics also helps with that, and we can get into the math and the calculation of rates themselves and all of that. But for the most part, it either happens fast enough or it happens so slowly that in natural aqueous systems, aquatic systems, we don't really have to worry about it too much. Or perhaps we're just ever so slightly off equilibrium and it would just take a long time to get to there. That it's okay to assume in many cases that we're already there. As you'll see when I do the pH stuff, it happens very quickly. Okay, so last time I talked about the pH. Just going to quickly gloss over this now. See the last video if you need more. The P for pH is acting a lot like kind of a function. It just means negative log of whatever follows it. So we can do pH, we could do pK, and you'll see that a lot for maybe the dissociation constant for an acid. We could do pKw, should be 14, because kW equals 10 to the minus 14. So you hopefully get the picture that this is an operator that acts on whatever comes after it, right? So we can do pH, we can do pOH. Doesn't really matter. It's the negative log of x. Px is negative log of x. And for the case of pH, what we're talking about is the molar concentration. So we're using brackets. One other thing to highlight here is because Kw is 10 to the minus 14, that sets our pH scale from 0 to 14, because we also know from our conversation a minute ago about the equilibrium equation here that the Kw is equal to H plus times OH minus. So if that holds true, then at a neutral pH, we have the same amount of acid as we have base. And we can kind of describe the H plus as acid and the OH minus as base. That means a neutral condition, they're equal, which means they're each equal to 10 to the minus 7. Okay, and that all works out mathematically because 10 to the minus 7 squared, or times itself, is equal to 10 to the minus 14. So all of that checks out and ends up making a lot of good logical sense when we stop and think about it. Okay, so on to thermodynamics then. And what I'm going to do here is try to give you from the big picture down to, okay, what specifics do we need to handle with thermodynamics in order to understand the equilibria. Next time we'll get into some practice. We'll have an in-person class next week, I hope. And so then we can work a few things together and I can see your faces and say, oh, okay, everybody looks utterly confused. I must have said something weird, or whatever the case may be. So what I'm going to do is try to paint the big picture. You've hopefully seen a lot of this in Gen Chem or other places already. And then get down to, okay, what are the pieces we need to put together in order to start solving for equilibrium constants for chemistry. That'll give us a foundation for the rest of the class to really build on and say, okay, well, we know based on the principles of the chemistry, we could find this K, this equilibrium constant, given the properties of whatever chemicals are reacting, and build from there. Okay, so thermodynamics. We can look at the name itself, thermo, the Latin root there. You think thermometer and many other words. It's basically temperature, right? And dynamics, that's a word we use, kind of motion or activity, right? So thermodynamics is kind of that science that relates to how heat and energy is transferred or preserved or manipulated, all that kind of stuff. So equilibrium we can define as the state where we reach a minimum energy level. So when the rates are going, when the rates become equal, that's the most energetically favorable place to be. That's why it was pushed to that spot. From the example video, you could see that the beakers could carry some certain amount, and part of that was, well, how high were these, and how much could the water be contained when dipped. That motion of dipping the beakers in had something to do with it, getting that energy level matching. Okay, so Gibbs free energy, you've heard it before. This is G. This is the amount of energy for a system at a constant temperature and pressure. So, and really this is in the context of kind of chemistry. So this doesn't really, the temperature and pressure maybe kind of indicates some aspects of like the physical energy, but we're not really saying that my glass of water has more energy here than here. There is that gravity, potential energy from gravity. That's not really what we're talking about. We're talking about within the chemistry of that water and whatever's in it on its own. And so we describe Gibbs free energy then because we need some way to talk about how much energy does this system have and how much energy might a reaction consume or give, or what is the energy involved with a reaction of two different chemicals together in a system. So then we have enthalpy, and enthalpy is basically the heat content of that system. So if you look outside, there's probably some snow on the ground still, at least in shady spots. And that snow has some sort of heat content, and it's as it heats up, it's melting, and that there's going to be a change in enthalpy during that process. Entropy is a bit different. This is, in a way, the amount of disorder, how much chaos, how much randomness is in a system. And one definition describes it as the amount of energy in a system that is not actually available to do any useful stuff. Can't do any work. It can't really cause anything to happen. It's just random motion. So that is often described as S, enthalpy as H. And so we will find a definition, and we'll look at it in a moment, where the Gibbs free energy is equal to the combination of enthalpy and entropy in a system. Now we're talking about systems, so I'm going to give a brief overview of the different types of systems and a few definitions we might see when we're dealing with thermodynamics. I don't want to get too far into this, but I just wanted to comment on it. Certainly the book goes into a little more depth on all of this. But we could think of an isolated system that cannot exchange anything with its surroundings. Heat, work, matter, nothing. Nothing can be exchanged. I don't love their example. They say the entire universe is the example. So assuming that there is some boundary there, it can't exchange stuff with other universes or whatever. That's just a little hard to think about. I would prefer to say it's a little bit of an ideal case, but if you had a perfectly sealed cooler or vacuum, like a vacuum chamber, there's a fancy word called a dewar. This is a vessel, kind of like a mug to keep something hot or cold, except it's used for like liquid nitrogen, things like that. So it's extremely cold. And the theory is you have a system where, and this is actually very similar to a cooler, right? To like a cooler, an ice chest kind of cooler. What you want to do is have a system that's double walled and then make a vacuum in between so that the entire structure might look something like that. And if you put a vacuum in here, nothing, so that there's kind of nothing in there as best you can make it. And of course you also want to seal it, right, with a lid that kind of does the same thing. But if you had an ideal version of that, you could isolate it so that there can be no transfer of materials across. That doesn't happen because it has walls. And there's no transfer of heat because the heat can't touch anything else next to it. Now, of course, we just have to use our imagination to think that we could do something perfect, because realistically there is some material that is on the outside of, even like a donut would have the outside of material on the edge allowing some heat transfer. So we can't really make one, which is probably why they're using the universe as the example, but we could imagine one, there's just no transfer. Anyway, that's a whole lot of focus on something that's not super important here. Adiabatic systems, they cannot exchange heat or matter with their surroundings, but they can exchange work. So this might be like a piston in a car engine would probably be described that way, because theoretically they're not exchanging too much heat. Most of that heat should be just going into the expansion of the gas. So their example is then if you take a parcel of air, so you just arbitrarily define some chunk of air that's outside, as it expands or goes somewhere, it could expand, which does work, even though it might not exchange heat or the air itself with its surroundings. Or at least you could make some assumptions that a system could work that way. Okay, a closed system, this is a little more like laboratory setting. So the water in my cup here, we'll see I put just a little bit of vinegar in a little measuring cup here for my demonstration. That would be a closed system. It's not exchanging matter with its surroundings, but it probably could exchange energy. And it can change chemical composition, therefore. Okay, open systems, that's open to exchanging both. Most environmental systems we could call open. Now, if you think of like deep in the ocean, maybe that would be a little more like a closed system. So we can imagine certain situations in nature where a piece or a component might be acting a little bit more like one or the other. Okay, but these definitions, the reason I'm bringing them up is because one thing you see in all of these is some reference to pressure or temperature or the number of moles, so the matter, and for moles, or maybe volume. And as I write these out, you probably remember from if you learned probably learned this in EVEG 2000. We have the ideal gas law, PV equals nRT. So temperature, the number of moles, the volume, and pressure. R is the ideal gas constant. And it's a very much a thermodynamic definition, this ideal gas law. So as we think of chemistry and chemical reactions, many of these parameters are going to be important in one way or another as we consider them. Okay, so briefly, the three laws of thermodynamics. I saw even our book was saying that some people might say there's a zeroth law, but it kind of calls on the others a little bit circular. So we'll just say the standard three here. The first one is that we have conservation of energy. You could be a little fancier with the terminology, and the book's text is here, talking about it in an adiabatic process, blah, 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 blah. The second law is really what we're going to be making the most use of. That says total entropy of an isolated system always increases. So their definition of the isolated system is the universe. In our case, we're going to do a lot of problems where we kind of assume that our chemistry is isolated to that problem and it's an isolated system. So this will hold true for a lot of what we work with. Entropy cannot spontaneously decrease, basically. And that'll make a lot of sense when you stop and think about entropy in general. If you make a nice latte and you put some cream and you start making the little a pretty little picture on the top of the latte, and it's like you make a little design in it or whatever. How many of you have done that? Anybody? Well, I guarantee you it's never going to spontaneously do that and make something that's ordered, but it will spontaneously become less and less ordered over time. So the design will spread and the entropy will take over. Same thing as if you just simply mix some cream into coffee, you'll see at first the mixing is not, if you're not stirring it, there's limited mixing, but over time the entropy will increase. The things will mix together. It's never going to go backwards from that. So that's kind of what that's talking about. Third law, the entropy of a pure crystalline solid at zero is zero at 0 Kelvin. So 0 Kelvin, this is absolute zero. Kelvin being our metric system for temperature. So we call this absolute zero. All right, and most of our thermodynamics, by the way, will be in Kelvin, so keep that in mind. Okay, so how do we do some calculations and what do they mean? We're going to start with Gibbs free energy, and G is our term for Gibbs free energy, and that relates to the heat and the temperature, the entropy, all that, in the following manner. So G, the Gibbs free energy, is equal to the enthalpy. This is kind of that heat content minus the temperature times the entropy. Typically, these are going to be in kilojoules per mole units and kelvins for temperature. So then when we look at a system where we have some change, Now the delta, this is kind of implying we've got some sort of shift or reaction involved. So when we look at reactions, we're often looking at the delta G, what happens before and after, or as we'll see, what happens if we take the G of the products minus the G of the reactants as our delta G. So the change in G would be equal to the change in enthalpy minus temperature times the change in entropy. So we see that entropy and enthalpy can change, and that can explain any changes in energy over here. T we could keep constant. Of course, if it somehow did not stay constant, that would also affect the system. So in terms of what it means, delta G tells us something about whether or not this can spontaneously occur. So when delta G is negative, that means the reaction, so I have this on another slide in a moment, but we'll say that this is equal to G of the products minus G of the reactants. So if G is negative, that means the energy of the reactants is larger than the energy of the products. And so it's favoring the reactants and heading towards the reactants. That means it's spontaneous. So this essentially means G of the products is smaller than G of the reactants, if I did that right. Okay, when G is equal to 0, we have reached that equilibrium point where everything's happily at the same value. They're going back and forth at the same level. Then when G is greater than 0, it's not spontaneous. You would have to add some energy to make this happen. It's not that it can't happen, it's just that it won't spontaneously happen. Okay, and we're going to work towards kind of understanding what goes into these other equations that I have here, and kind of doing a little bit of derivation, but more so just kind of stepping through what the meaning is. Why do we end up there, and how do all these concepts about thermodynamics tell us something about chemistry in the first place? Like, what's really that connection? Okay, but one more comment here. One thing we can do with our equation, now that we know, so with this equation here, now that we know that a negative delta G means it's spontaneous, we could look at the different conditions of delta H and delta S, or really of T delta S, and identify what's going to happen in our system. So we have this little box diagram here where we have two different conditions for delta H. So how does the enthalpy of the system change? Is it a change that's negative, or is it a change that's positive? And how does the entropy change? Is it a positive change or a negative change? Now, entropy can decrease, right? It is possible to decrease. Let's say if you freeze water, you have taken water molecules that are wandering around in solution quite randomly, and now you've ordered them into some crystal structure. That has decreased the entropy. Now, is that reaction going to be spontaneous? Well, under certain conditions, you saw just Tuesday, right? We had snow falling. Certain conditions, that does happen spontaneously. It will happen. So when delta H is less than 0 and delta S is greater than 0, delta G is always spontaneous. And we can simply see that when we take a look at delta G is equal to, the first part is delta H. If this one is negative, and then we have a minus, so I'm just going to put delta H here and T delta S. Right, so this is our equation, and I'm going to put in a little value here, and a little value here. So under the first condition, we have a negative delta H and a positive value here. Clearly, the net delta G here is going to be negative because we have a negative minus a positive. So it gets even more negative. So from that, we see for sure this box is negative. We could go to the very opposite end and say if this is a positive minus a negative, that is just always, always positive. There's nothing negative that could come of that. So this one in the opposite corner is certainly always positive. Now, if we have the edge cases here, if we'll start on the first column, if delta H is less than 0, so we have negative, and then we have minus a negative, so this is, I'm just going to draw this over here actually. This is a negative minus a negative. Just going to give each box their own little spot. So a negative minus a negative, it could become positive because the double negative makes it so that we have a negative plus something. But it's only going to be spontaneous when T is high. I'm sorry, did I do that right? This is a positive. Yeah. And this one was the negative, right? No. Sorry. So when delta H is positive, this is a positive, minus a negative. Okay, so we are minus a positive, sorry. Okay. Feel free to correct me, by the way. All right. So if we have a positive minus a positive, there's a chance that's negative, a net negative, right? Because it could be 10 minus 5, or it could be 10 minus 20. You know, that will depend. And so what we can look at then is the temperature term is going to dictate whether or not this is a spontaneous reaction. So when the temperature times delta S is large, this will become a negative value because this piece has to be a large positive in order for the net equation to become negative. So that means at high temperatures, that tends to happen spontaneously. The reverse will be true over here when we take a negative minus a negative, right? In this case, we have a negative, but then we are effectively adding something. And so if it's a high enough temperature, the second term here, the T delta S, will become too large, and we're just going to get no more spontaneity for the reaction. So this one will happen spontaneously at a low temperature. Okay, so I wanted to show this to kind of give us a framework to help us understand a little better what this whole thing could mean in practice. That we can understand certain times a chemical reaction will be spontaneous and certain times it will not be. So some will never be spontaneous at any temperature. Some, when you make it cold enough, we form ice. When you heat it enough, we form water vapor, or whatever the reaction might be. Okay. Now, in order to really compare different systems with the Gibbs free energy and several of the other thermodynamic concepts, we need a default value. And that's what we call standard temperature and pressure, or a standard state, or a standard Gibbs free energy. And we're going to denote that standard often with a little degrees symbol. So this is essentially a default that we assume, and why not just use room temperature? So we use essentially 25 Celsius. If you recall, to convert from Celsius to kelvins, we add 273.15. So C temperature in kelvins plus that equals temperature temperature in degrees Celsius, plus 273.15 gives us temperature in kelvins. Okay, so 25 Celsius is then 298.15 kelvins and 1 atmosphere. So that's our standard state. Now, technically speaking, we could decide on a new standard state. We would just have to adjust a whole bunch of calculations, and anytime we take from some reference book or appendix or table or whatever, we would have to do conversions to use our new standard. But the standard itself is kind of arbitrary. So it's room temperature and 1 atmosphere, which that's basically the typical amount of pressure coming from the atmosphere when we are at sea level. Okay, so that's the standard convention. Some of this becomes really obvious for chemistry involving gases, but the same principles do apply to water as well, so we still need to use them. But you can imagine that in the gas phase, if you have a very low pressure, the molecules are just not going to see each other very often. They're floating around, but there's so little pressure, they're not going to see each other, so that's going to make a big difference on that system. And the whole thing is compressible. Water is relatively incompressible, but the pressure still will have an impact. So we still need to assume and define a standard temperature pressure. Okay, so when we see the delta G with a little naught or with the degree sign, that's the standard change in Gibbs free energy, meaning the standard being what we see at STP, at 25 Celsius and 1 atmosphere. We also use this for other conventions like chemical potential that we'll talk about in a moment, and you'll probably see it in several other locations as well. Okay, so chemical potential. This term is part of how we define G itself, or how we arrive at G in terms of understanding what is the chemistry, like what is the energy within this chemical, or that's possible with this chemical reaction. So mu here is the chemical potential, and we ought to think about it a lot like gravitational potential, right? We can take a ball and raise it to some height, and now we've increased its potential energy. On a chemistry sense, mu is similar, right? We can raise the potential to a certain amount, and based on the height, in this case, based on the chemistry, it may have some more or less energy. It doesn't actually matter what, how heavy that ball is directly. You've still done the same different height change. In the chemistry world, mu is kind of like that in the sense, or kind of like temperature might be a better example. You could have one tiny, tiny, tiny drop of water that is extremely, extremely hot, or you could have an entire pot of boiling water that's extremely hot. Now, physically, the difference matters, right? One of those, you might feel it, but it's not going to give you a lasting burn because it just didn't have enough heat in it. The other could give you a severe burn if you splashed it on you. So temperature is this intensive, is what it's called, property where it doesn't really matter how much you have of it, it's still defined on a certain threshold. Well, mu is the same way. We're going to define it. So G is the combination of how much you have and how energetic, how hot is it. So mu we define as delta G per delta N, or basically the amount of Gibbs free energy per mole. So this is the energy, the Gibbs free energy per mole, essentially. So chemical potential then, if you have a system with many moles in it, of course it has a large total energy, but the energy per moles doesn't change. So that's perhaps a lot to say just to describe it. It's almost exactly the same thing as G, except G um, is more of a bulk term that will be larger with a larger system. Okay, the way we relate these to thermodynamics, they both relate in approximately the same way, where if we have some chemical potential for a species I, we can say that that's going to be equal to the chemical potential at a standard state plus something that happens over here. Okay, and that something that's happening is going to relate to the reaction. So some sort of chemical reaction. And we need to dive into that a little bit. What we see, first of all, is R is the ideal gas constant. Talked about that already. T, of course, is temperature, if that wasn't obvious. Should be in kelvins. And then the natural log of A, this is the activity of I, so we need to talk about activity, but essentially that's going to be the concentration of I under ideal conditions. So what we see then is that the um, the potential energy of the system is equal to the potential energy under the standard conditions plus the current temperature times the R times the natural log of that, effectively the concentration. But eventually we could do this for an entire system or an entire reaction and have delta here. So delta G would be equal to delta G naught plus RT natural log of Q. And as we'll talk about, Q is basically the reaction quotient. We described the products over the reactants and how to calculate that. That's where the Q is going. So we're getting there. I'm going to come back and we'll see a few more equations here, but we're working towards deriving all of that and connecting these two pieces. Okay, just a little more on chemical potential itself to help us really understand what's going on. I already described a little bit the potential energy analogy. So if we think of potential energy like a ball on a staircase, for example, if we lifted it up to some height, it has a potential energy of the acceleration due to gravity g times height, right? Now, we could say that sea level is down here, or we could say sea level is right here, or wherever. And so in this little diagram, going up is increasing h and therefore increasing the potential energy. And this is potential energy per unit mass. So that's why in this example, that's why the mass doesn't really matter, because we're saying per mass. Per mass, it's g times h. Of course, to get that raw energy, we'd multiply that by mass. Okay, so we can define, for example, a little sealed compartment inside the staircase and say if the ball was right here, then that's the standard condition. So if we then take it out of that condition and drop it, it could go further down, that it could go negative, right? We could have a negative potential energy because it would take energy to lift it back up. Or if we took it upward, then it would have a positive potential energy. So all of that to say is it's a little bit arbitrary, just like 25 Celsius is a little bit arbitrary. There are places in the world where we are below sea level and we're not underwater, right? New Orleans, for example, is at least, 20, 30 feet under below sea level in some places. And we've obviously kept the ocean out from that. So there are moments where even physically that makes sense. So chemically speaking, the chemical potential, is quite similar, where we have increasing activity, usually concentration, of our system could put us at a higher value for mu. And if you notice here, the activity, if we increase that, that would increase this entire equation. It's in relation to some standard state, some maybe standard temperature and pressure. And we could go negative, right? So very similar deal here. It's a potential energy per mole, just like the potential energy per unit mass concept right here. Okay, is that making some sense? Any questions on that? All right. Okay, so this I'm going to take this analogy just a little bit further. In one of the books that I took some material from, I don't think this is our book, it gives an analogy of New York City and the Empire State Building and oxygen. Okay, so in the physical system, we could take a look at a boat at the sea level in New York City at a dock. The potential energy would be gravity times 0. In an analogous chemical system, we have pure oxygen gas, O2, at 25 Celsius and 1 atmosphere. And we define the chemical potential in that gaseous state as 0. Now, keep in mind, that's if we had 1 atmosphere worth of oxygen gas, and we actually only have, 21% of our atmosphere is oxygen. So even though that's a very baseline condition, that's technically a little different than sea level, what we breathe. Okay, so then let's take the next line and say some other case that might be interesting. Let's take the lobby of some building. Maybe that's G times 14. So maybe we're 14 stories up or 14 meters above sea level or something like that. This might be like taking the oxygen scenario again, but saying that this is going to be an aqueous at 1 molar, 1 molal probably, if the lowercase m. And then we could define the standard energy for oxygen under those conditions. We look this up in a table and find that's the value, 16.32 kilojoules per mole. And then maybe we take the elevator up further and we go up or down. We could say we're going to move somewhere else, and now we go up or down in h, the height, that changes our energy. And in the chemical system, we could change the amount of concentration of oxygen. We go up or down, and here's how it looks. We have mu naught equals, mu equals mu naught plus RT ln of x in this case, right? So we took from here and put it there, and then added whatever change we made to the concentration. So that's, practically speaking, how the calculations go about it. And you'll see that if we took the potential energy example, the G times H, that's the gravity times height, and we changed the height, all we have to do is look at the standard to know what we are at currently, and maybe it would be good to say, I don't know, current or something. Like this, saying it this way where these two are the same value, look to be the same value, is kind of confusing, right? So I'm just going to add that there. But to understand where we are now, all we have to do is look at where we started plus what we changed, right? So that's what this system is showing. And that's exactly how our Gibbs free energy equation works, or our chemical potential equation works. So mu equals mu naught plus RT ln of x, right there. Okay, so let's try to connect this then to equilibrium constants. Well, thermodynamics tells us about reaction conditions. Is it spontaneous? How much energy is there? What's the deal with all of that? What kind of states are involved with entropy? And we know that equilibrium is reached when two reactions find that lowest combined energy. So we can define the delta G for a reaction as the delta G for the products minus the delta G for the reactants. This is how we relate the G, the thermodynamic stuff, to the equilibrium. You'll remember when we defined a K, we were saying it's products over reactants. And so you can kind of see a similar scheme here with products and reactants, right? So we're going to go through a couple slides with derivations. I'm just kind of pointing us in that direction right here. And as I mentioned, we're going to use standard states as comparisons. So those delta G naughts and the mu naught. These standard states have been found experimentally, and we can take a lookup table and see so many of them just listed there for us. So given that we can make use of that, and we can compare a system, are we at standard temperature pressure? Do we need to make some change? That's all good. We can go look stuff up. So we're almost ready to make the connection directly, but there's one more caveat we have to mention here, and that is activity. I already alluded to it, but activity is not always the same thing as concentration. Most of this class we will assume that, but briefly today I'm going to describe it, and next time we're going to go into a few basic calculations, how we might calculate activity for a given condition. But if you think about gas for a moment, in a vacuum, there are very few gas molecules floating around. We've lowered the pressure so much that there's very few around. So it's very infrequent that two gas molecules will have some action together. They'll encounter one another and go through some reaction. If you had a very high pressure environment, they're going to be very active. So in the same type of situation, the same type of thinking, we can see that the activity of a chemical environment in an aqueous system may also be, the activity may be impacted by the concentration we have. And sometimes that activity is actually decreased based on having too much stuff, then we get some interferences. Okay, so concentration versus action is really the deal here. And you'll notice we put curly brackets for activity and square brackets for concentration in moles per liter. So the change here is that the activity of I is equal to, we can write it as AI, so the activity of I. And we can say that's equal to the concentration of I times this coefficient. And this coefficient is simply a dimensionless activity coefficient. So we're going to, next time, look at a few options of how to calculate this gamma I. We'll just say it can be calculated or estimated. A lot of times we'll use ionic strength, so what's the total amount of ions in solution, to get some approximation for that to do our chemistry calculations. But in general, if we have a dilute water, this gamma tends to be about 1. So a lot of times we can ignore it. Because if it's 1, then our activity is the concentration. It could never be 0 or less than 0, right? We'll never have a 0 activity or a negative activity. All right, we can go a little fancier with why it's defined this way, and even use some, you'll see the little standard state sort of thing. But I'm not even going to really say anything more than this. It's just, we can elaborate on that, and there's some hypothetical standard state of the activity. Don't worry about it. Maybe I should just delete this slide. It's just saying we could go into the thermodynamics and describe in a little more depth, but we don't really need to. And this gamma is still going to be just as useful for us. Okay, briefly, here's a table that kind of summarizes what types of activities we might see in the environment. So to take a look at how species I is behaving, it will behave less concentrated than it really is when the activity is less than 1. So when the curly bracket I is less than the square bracket I. Sometimes we'll have a condition where it might behave more strongly. It'll be reacting more rapidly than we would expect it. So the activity is greater than 1, or the activity coefficient is greater than 1. I think that's pretty rare. I don't hear about that very often. And then if it's ideal behavior in a dilute condition, it's right here. So I'm just going to say we are often going to assume that. We're going to get equipped to calculate the activity coefficients so we can know that we can do that, but we often don't need to. Okay. Now, how do we apply activity to our equilibrium constants? Well, if this is our equation normally that we had here, all we have to do to make it proper is put curly brackets, right? So that it becomes this when we are accounting for activity the right way, or like properly, and doing everything very precisely. Now, if we have a dilute solution and we can safely assume that all of these are 1, that's where we get this equation that we started with. So most of the time we're going to do that, but like I said, we're going to figure out how to calculate each activity coefficient, which, by the way, can be different from each chemical from one to the other. The activity will depend on how they interact with water, how they interact with other stuff around in water. So we will see that could make an impact. Okay, but setting that aside for a moment, aside from the fact that we will see activity in our equations sometimes, but putting that aside in terms of how we get that, here's where we connect the dots of delta G and the equilibrium constants. Because it's really the equilibrium constants that we need in order to understand and characterize our chemical systems. So we can calculate the change in G based on all the mu values, all the chemical potential values before or after some reaction. So we already described that delta G can be defined in terms of the number of moles and the chemical potential. And in fact, what we said was the chemical potential was the del G del N, right? So that's the G per mole. So we can just rearrange that a little bit and get G in terms of the moles and the mu. So that's what we're seeing here. We could look at delta G for a system and try to understand what's happening there. And we can do the sum of each species within the system, the delta G for that given species, is equal to the N times the U of the final minus the initial. So final being the products, and the initial being the reactants. Okay, so and the whole summation thing, that's just saying we're going to do it for each piece of the puzzle. So with that, and the fact that we know we have some definition for the mu, we can insert the thermodynamic definition of mu, which was right here, and expand that a bit and say, oh, okay, now we have delta G in terms of the number of moles, the standard potential, the thermodynamic components, and the concentration. Activity, really, but as we said, that's going to relate closely to concentration. And we do that before and after. So I'm going to skip some derivation here, but basically we can expand all of these equations and say that, okay, for each different reactant, if we have A plus B equals to C and D, we recognize we can have a lot of stuff going on. We can sum that up into a system using this little VI here as a way to shortcut doing the whole sequence. That'll make a little more sense in a moment. So once we have that component, we can go from this V into a Q. And the Q is the reaction quotient, which was the products over the reactants. Now, to be correct, we will describe this in curly brackets. Say the activity of the products over the activity of the reactants. And that all puts it together in the sense that we have delta G. The current delta G is equal to some standard state that we had plus some reaction that occurred. That's our RT ln Q. So that reaction quotient, sometimes described this way, it's that product of all the products over the reactants. And we raise, basically it's just saying this right here. Okay, so all of that to say we can get delta G in terms of what's going on with our equilibrium constant, because this is essentially our equilibrium constant. Or it at least relates to it. Okay, I think this is my last slide, and then I'm going to do a quick little chemistry demo for you to have a little bit of fun. So this is saying, like, these are the types of equations we're going to have on an equation sheet, and I just want to try to connect all the remaining dots here. So we have those previous equations. We notice that if Q is 1, that would mean RT ln of 1. This goes to 0 because the natural log of 1 is 0. So that means that when we have 1 for the quotient, all of the activities are 1. It's 1 divided by 1, all of that. Then delta G is equal to delta G naught. That's the standard state. We're at equilibrium at the standard state. So nothing has happened or moved. So that's very handy, because then we can say, well, at equilibrium, delta G is 0, then Q is really equal to K. So I should not quite say Q is equal to K. We'll just erase that and leave it here, because here's where we get K. So if Q is 1, if delta G is 0, then Q is equal to K. That's what I'm trying to say. So we could say then, when we're at equilibrium, delta G is 0, so 0 will be equal to delta G naught plus RT ln of K. We can rewrite this, as you probably have seen before, as delta G naught is equal to negative RT ln K. Okay, so that's where our key equations for this class are coming from. If we want to change from natural log to log base 10, we have to do some small conversion there. It's not a big deal, but that's just the place where it shows up. Okay, so we're going to get, we'll have these equations in your exam, and we can actually combine these two back together and say delta G is equal to 2.303 RT log of Q over K. So don't know if we really need that one too often, but these are kind of the governing equations we can use in order to do these thermodynamic calculations and connect it to our equilibrium reactions. All right, so stay here for just a moment. And what I'm going to do, sure, that's fine background. What I'm going to do is move my camera a little bit. All right. So I've got a little 5 milliliter vial here, and I'm going to go fill it up with water from my aquarium and test the pH. So I've got a little pH testing kit. Basically going to follow the instructions here, adding drops of that. I have a little pH up. This is essentially base that I can use to add and increase the pH if I needed to. I ran out of the pH down, which is sulfuric acid, so I've got some vinegar that should probably do the trick. That's just coming from some multi-purpose white vinegar, basically. All right, and when I do check the pH, we'll compare it to a little chart here, and we'll see the color change based on that. So, well, I guess if you'd like to see me go grab from my aquarium. All right. So we've got about 5 milliliters of water there. And the little instructions say to add 3 drops. So I'm going to go ahead and do that. And this should change color based on the pH of the water. I'm going to see if I can get a better background there for you. Kind of see the color change. It's going to fall. Okay, so you can see, and again, as always, feel free to comment if you find this interesting. You can see the entropy is starting to increase in the system, right? It's starting to mix. So I'm going to mix it well. And we have a nice blue color. No surprise to me. I actually know that the water we have here, and for my aquarium, I just basically get tap water and dechlorinate it, or don't add enough so that it's not too much chlorine at once. It tends to be pretty basic, and in my aquarium it tends to be pretty basic. So we see it's at 7.6 or higher, if you could read that. So probably I ought to add some acid to the system, and the fish might be a little happier, is my conclusion there. But what I can do right now is add a little bit of vinegar. Is probably not the right kind of acid to add for the aquarium, but a little bit of something like sulfuric acid that's just going to adjust the pH and not do too much else would probably be all right. So what I'm going to do now is just add, if I can, just a couple drops of this vinegar, and it should decrease the pH a good bit, and we'll see how quickly this goes to a new equilibrium. Okay, so you can see immediately, and as it's mixing, it is changing to a more yellow color. You can actually see a little bit of blue still in it because it hasn't fully mixed yet. It's kind of neat. But as soon as I mix it up, we can see clearly that we just went to the other side of the pH scale, and now we are decidedly less than pH 6. I mean, maybe it's exactly pH 6, but I kind of doubt that. Okay, so then just to continue, do a little bit more, we can say, all right, well, we have this pH up. This is probably sodium hydroxide, maybe potassium hydroxide, something like that. Some other base. I'll be careful. I probably should theoretically use safety glasses here, but should be okay. So added 1 drop, and we see immediately a little bit of blue shot through the system. Didn't really convert the whole thing yet, so I'm going to do another. I'm just going to add this until we see a significant change. Maybe that's it. You can see at the bottom, the base is sort of accumulating there. So mix it a little bit, splash it all over my desk, and still have too much acid. So this demonstration, by the way, will make more and more sense the longer we go through our class, as we learn more about buffering capacity, titration, things like that. So hopefully this will be good to keep in mind during the semester. I guess I could certainly bring it to class too. Okay, so now we are blue and yellow. Let's get it mixed better. Now we've reached something that's closer to neutral. So it's a little hard to see maybe on the camera, but we are somewhere pretty close to pH 7, maybe 6.8, maybe 7. Okay, so pretty neat. Just out of curiosity, the last thing I'm going to do is take my water bottle and check the pH in the water. I'm just going to dump this into my vinegar. We'll certainly turn that yellow. And in order to rinse, I'm just going to use my water in my glass here. Just give it a bit of a rinse. And one more time, I'm going to fill it up to about 5 milliliter mark. Too much. Okay. Should be close enough. And maybe I should use 2 hands. So I think this is going to be probably a little bit above the scale for our pH scale again. Typically, our water distribution systems want to operate a little bit basic to avoid any corrosion of the pipes. We'd much rather have the opposite of corrosion, precipitation. So we'll talk about that later in the semester. But I'm going to add 3 drops here, and we'll see what the pH of our water looks like. Quite blue there. Yeah, perhaps even more blue than the aquarium. All right, so our tap water is definitely pH 8 or so. All right, well, that'll do it for the class. Thanks for joining. Please let me know if you enjoyed that. And to answer your question, I'm sorry I missed that till just now. I have there's probably 8 little tiny fish in there. You can kind of see one of them right there floating around. And they're actually mostly from just the pond outside, little sunfish. If I had a second webcam, maybe I would bring it over there and give you the fish cam instead of my face. All right. At any rate, have a great day, and I'll see you guys in person on Tuesday.